Physical Science 20, Heat Lesson 2, Latent Heat and Specific Heat Capacity. This lesson goes along with the H3 and H4 assignment. There are situations when the addition or removal of heat does not cause a temperature change. Think of a glass of iced tea with ice cubes floating in it. Heat does enter the glass from the warmer room, but the temperature of the iced tea does not rise above 0 degrees Celsius as long as ice remains in the glass. This is because all the energy entering the glass is being applied to the ice cubes, transforming the ice into water. Once all the ice is melted, the drink will then begin to warm up to room temperature. So check out this experiment. I got my Bake-O-Matic, which is an oven I can put stuff in and heat it up. Pretty exciting. So I went out and I got a beaker full of snow from outside, placed inside the Bake-O-Matic. Also put a temperature gauge inside there and watched the snow melt, turn into water, and then the water warmed up till it started to boil, then it evaporated, and then I had a Bake-O-Matic full of steam. I guess there's nothing too exciting about that. But let's check out the device that was measuring the temperature. We'll look at a graph right next to the Bake-O-Matic as it heats up the snow. So let's do that again. The Bake-O-Matic again has a beaker full of snow from outside and a temperature probe. And the temperature probe is going to relay the temperature to my graphing system on the right side of the screen. Now the snow came from outside and it's really cold out today. And the temperature probe says that the temperature of the snow is minus 21 degrees Celsius. I will now turn on my Bake-O-Matic. And when I turn it on, the snow starts to increase in temperature. Once it hit 0 degrees Celsius, the snow started to melt. And the temperature stayed at 0 degrees Celsius until all the snow had melted. Once that happened, the water started to increase in temperature until it hit 100 degrees Celsius. It started to boil then, and it stayed at 100 degrees Celsius until all the water had evaporated. Once the water all evaporated, now I only have steam, and the steam started to increase in temperature. So the temperature increased as a solid, the temperature increased when it was a liquid, and the temperature increased when it was a gas. But the temperature did not change when it was melting, and the temperature also remained constant when it was boiling. The latent heat, symbolized by a capital L, is the heat per kilogram that must be added or removed when a substance changes from one phase to another at a constant temperature. There are three types of phase changes: fusion, vaporization, and sublimation. LF is the latent heat of fusion, and that is when we go from a solid to a liquid or from a liquid to a solid. So when things melt or they freeze. LV is the latent heat of vaporization, used when we go from a liquid to a gas or from a gas to a liquid. And the less used one is the latent heat of sublimation. And that's when we go from a solid to a gas or from a gas to a solid. Not too common, but we know it does occur because living here in Saskatchewan, we see snow on the highway. And even though the temperature may not go above 0, the roads eventually clear because the solid snow slowly moves into the gas phase. MP is the melting point. This is the temperature at which the material goes from a solid to a liquid or a liquid to a solid. So if we look at the very bottom, we have water, and we know that the melting point of water is 0 degrees Celsius. That is also the freezing point if the temperature is decreasing. BP is the boiling point. This is the temperature at which the material goes from a liquid to a gas or a gas to a liquid. Again, if we look at water at the very bottom of the chart, we see that water boils at 100 degrees Celsius. That's the boiling point of water on a clear day if you're by the ocean. Being that we are at a higher elevation, the boiling point is actually lower than 100 degrees, more around 97 degrees in Saskatchewan. LF is the latent heat of fusion. This is the amount of energy needed to transform a kilogram of that material from a solid to a liquid state, or energy that is removed from a kilogram of material when we go from a liquid to a solid state. I want you to add to your pink sheet solid to liquid over top of LF. LV is the latent heat of vaporization. This is the amount of energy needed to transform a kilogram of that material from a liquid to a gaseous state, or energy that is removed when the kilogram of material goes from the gas to the liquid state. So over top of LV, I want you to put a two-way arrow showing that LV is used when we go from liquid to gas or gas to liquid. The formula for latent heat calculations is simpler than that of specific heat capacity, since there is not a temperature term. This is because the temperature of a substance is constant while it is undergoing a phase change. So our formula is simply Q equals mL. Q represents the change in heat. It's measured in joules. M is your mass measured in kilograms. And L is the latent heat. It's the value that comes from our table. And again, LF, if we're going from a solid to a liquid or liquid to solid, or LV, if we're going from a liquid to a gas or gas to a liquid. And latent heat is measured in kilograms per joule. Example 1, how much energy does it take to melt a 23.0 gram gold ring? We are looking for energy, so that means we're looking for Q. Heat is symbolized by a capital Q. We're also told it's a 23.0 gram gold ring, so our mass is 23.0 grams, which I will convert to kilograms, because if I look at the value for LF or LV, it's measured in joules per kilogram. So we convert to kilograms so that units will be able to factor out when we do our calculations. We also know that the ring is made of gold and it is melting. So since it is melting, we are using LF. Again, the ring is made of gold, so that means we are using this number here as our LF value. So LF equals 6.28 times 10 to the 4 joules per kilogram. Our formula is Q equals mLF. We do not have to rearrange because it is already set up to solve for Q. So I just have to substitute my numbers into the equation. So Q equals 0.0230 kilograms multiplied by 6.28 times 10 to the 4 joules per kilogram. And that gives me 1,444.4 joules. I'm only allowed to have 3 significant figures in my answer. So that means my final answer is 1,440 joules. Example 2. What material loses 44 kilojoules of energy when 215 grams are converted from a liquid to a solid? If I'm looking for a specific material, I'm going to have to do a calculation, look at my data table, and see which substance has the number closest to what I've calculated. And in this case, since we're going from a liquid to a solid, we're going to calculate LF and see which substance has the value closest to the LF value I have calculated. We have 44 kilojoules. Kilojoules are used to measure energy, in this case heat energy. And since LF is measured in joules per kilogram, kilojoules will have to be converted to joules so that the units can factor out. Since joules are smaller, my number gets larger. So I have 44,000 joules. 215 grams is my mass. And since LF is measured in joules per kilogram, this will also have to be converted, and it's going to go from grams to kilograms. Since kilograms are larger, my number gets smaller. So I have 0.215 kilograms. The formula is Q equals mLF. To get LF by itself, I will have to divide both sides by m, so that the m's on the right-hand side factor out, leaving LF all by itself, and on the other side of the equation I have Q over m. I substitute my values in, run it through my calculator, and I get 204,658 joules per kilogram. The LF values are all times 10 to the 4. So if I want to compare what I have to what's on the data table, I will have to convert my number to a number that is times 10 to the 4. In which case, that will give me 20 times 10 to the 4 joules per kilogram. And the number closest to that value in the LF column is right here, 20.7 times 10 to the 4, which would be copper. So the material is copper. Two objects of the same mass and temperature may hold a different amount of heat. This is because they are molecularly different. Some materials rise in temperature greatly when heat is added to the object, like lead, and other materials require a lot of heat in order for their temperature to rise slightly, like water. To the right is a data table that you will find on your pink sheet. This outlines the amount of heat required in joules to raise the temperature of a kilogram of that substance by 1 degree Celsius. You can see the specific heat capacity of iron or steel is 452, whereas water has a specific heat capacity of 4,190. That means it is much more difficult to raise the temperature of water than it is for steel. In fact, since the number for water is 9 times larger than the number for steel, if we put a pan on the stove and added heat to it, within a short amount of time, an empty pan could potentially burn our hand because it heats up 9 times faster than if I put an equal amount of water on the stove, which makes sense because if I've ever heated water on the stove, I know it takes a long time for the water to heat up. The element is continuously pouring heat into the water, and I can keep putting my finger in and out of the water without burning myself. It takes quite a while for that water to heat up. The formula we use is Q equals MC delta T. Yeah, MC delta T. Yo, bring in the heat. Just call me Q. Q is heat, and it's measured in joules. M is mass, and it's measured in kilograms. C is the specific heat capacity of that material, and that will be found on the pink sheet in a data table. Delta T is the change in temperature. And remember, change is always final subtract initial. So our change in temperature is always our final temperature subtract our initial temperature. Example 3. 4 kilograms of water have been placed in a refrigerator to make ice water. If the water was initially 25 degrees Celsius and the refrigerator brings the water down to 5 degrees Celsius, how much energy did the refrigerator draw out of the picture of water? So I'm looking for the amount of heat that has been taken out of the picture of water. 4 kilograms is our mass. We're starting at 25 degrees Celsius, and in the end, the fridge is going to reduce the temperature down to 5 degrees Celsius. And we know that the specific heat capacity is 4,190 because we are told that this is water, so we can get the specific heat capacity from the data table. Now note the specific heat capacity of water depends on the temperature of the water. We will have to assume that it is 4,190 joules per kilogram degrees Celsius at all temperatures when doing calculations. But as water increases in temperature, the specific heat capacity does change. So for the calculation, Q equals MC delta T. I know M, I know C, but I don't know delta T. But I can find it because I know my initial and final temperatures. And change is always final subtract initial. So 5 subtract 25 gives me a change in temperature of 20 degrees Celsius. That's with two significant figures because while we're adding and subtracting, so we stack it in columns and draw a round off line, and it tells us that the 2 and the 0 are both significant figures. Now I can substitute my numbers into the equation. I run it through my calculator. Kilograms and kilograms factor out. Degrees Celsius and degrees Celsius factor out. So I get negative 334,880 joules, which could be written as negative 330,000 joules, or, since it's such a large number, negative 330 kilojoules. And that's the end of the lesson. You're good to start working on the H3 and H4 assignment.